Hello students, welcome to our channel Physics class. How are you all doing? Today we will study about the magnetic field that is generated due to the presence of electric current, that is a moving charge. So let us start first with the topic when we will study force between two parallel current carrying wires. So we take two current carrying conductors which are placed near to each other, and due to their electric current, there is a magnetic field which is produced. So first of all, I am drawing such two conductors. See, this is our conductor A and this is the second conductor B. So you can think them of as the current carrying wires which are placed at some distance, and the current which this first conductor is carrying is the current is represented with I, and since it corresponds to the first conductor A, so we write it down as IA. And the second conductor, it is also carrying some current, so current is represented with I, and since it is carried with the conductor B, so we write it down as IB. So these are the two conductors A and B carrying the currents IA and IB, and they are kept at some distance small d. That means the distance between these two parallel current carrying conductors is small d. Due to the flow of the electric current, there would be some magnetic field is produced. So let us say that the magnetic field which is produced by conductor A is represented with BA, and similarly the magnetic field which is produced by conductor B is magnetic field B with suffix B. So we want to find out these magnetic fields which is created by these two current carrying conductors. So since these are current carrying wires and they are having a circular symmetry, so we can use Ampere's circuital law. So what is the law? That B dot dl is equal to mu naught I, that is Ampere's circuital law. If we want to calculate this magnetic field for the conductor A, so we can write it down as BA, and here you have to use a cylindrical symmetry, and if you make an imaginary surface here, then you can take the cross section as 2 pi r, and since the distance between these two is d, so we can take this as d. So this is BA into 2 pi d, because we want to calculate magnetic field at a distance d. We want to calculate magnetic field. We want to calculate how the magnetic field which is produced by the current carrying conductor A is affecting the current carrying conductor B, and similarly how the magnetic field produced by B is affecting the conductor A. So let us go with the magnetic field which is produced by the conductor A. So it is at a distance d. So we'll take this radius as d. So B into 2 pi d is equal to mu naught, and the current is in the first conductor mu naught IA. So from here we can easily get the value of magnetic field produced by conductor A. This is equal to mu naught IA upon 2 pi d. That is simply we have calculated using Ampere's circuital law. So now we know the magnitude of magnetic field which is produced by current carrying conductor A, and from the similar ease we can calculate the direction. Similarly, we can calculate the direction of magnetic field very easily. So for that we use right hand rule, and from that we get that the direction of force, that is the magnetic force on B due to A, is downward. So here you can show it like this. It is in the downward, so you can show it here like this. So this is the field which is a magnetic field produced by A and which is acting on conductor B. So now we know the magnitude and now we know the direction. So we can calculate the force on conductor B which is due to this magnetic field. So now we want to calculate the force. So in order to calculate the force, we will take a small segment, say from here to here. We are taking only a small segment of this conductor B, and say that the length of the small segment is capital L. So this is small segment of length capital L, and we are calculating the force on this line segment capital L of conductor B due to magnetic field of A. So the force on segment L of B due to A. Now we know the formula of force. So this is force is equal to ILB. So this is I, L and B. So this force is on B due to A. So we write on tab PA. The current is flowing in conductor B, length is L, and magnetic field is produced by conductor A. And this is equal to, so this will be BA. Now put the value of BA. So that means F, BA force on B due to A will be current flowing in B, length of B, and magnetic field produced by A is mu naught IA upon 2 pi D. D the resistance between two conductors. So we get it as force on conductor B due to A is equal to mu naught upon 2 pi. So this is how we have calculated the force on the conductor B due to the magnetic field of A. In the similar terms, we can also calculate the force on conductor A due to the magnetic field produced by B. Because these are two current carrying conductors, so they will mutually affect each other. So similarly, we can calculate the force on segment L of conductor A due to conductor B. So if we come here, then magnetic field of B will be again mu naught IA upon 2 pi D. And if we calculate the force of A, force on A due to B, then it will be the same thing, but only the direction will be opposite. So directly you need not do all this calculation again, because we know that it will be similar. Only the way we have calculated the magnetic field of A and then force on B due to A. Similarly, we can calculate the magnetic field of B and the force of A and the force on A due to B. So these two will be exactly same, only the direction will be opposite. So we can say that the force on A due to B will be exactly equal and opposite to force of B due to A. So what we can conclude from this, that if we are having two current carrying conductors, then both these two conductors affect each other and the magnetic field is produced by each of the conductor. Then due to the magnetic field, the force on conductor A due to B will be exactly equal and opposite of force on B due to A. So since these two forces are equal and opposite, so what we conclude from this is, first thing we conclude that it is somewhere equal to Newton's action-reaction law. That for every action there is an equal and opposite reaction. So if this conductor B is exerting a force on A, and similarly the conductor A is exerting a force on B in the opposite direction, so we can compare it somewhere to the next Newton's action-reaction law. Second thing we can get out of it is that if there are two current carrying conductors, they are exerting force on each other and this force is exactly opposite to each other. That means these two conductors are attracting each other. And these two are parallel, the current flowing in them is parallel. So we say that two parallel currents attract each other. So this is very important a point, because whenever you get in your objective type questions, you are given with the two parallel currents, the current is flowing in the same direction and they are parallel to each other, then always remember that these two parallel currents will attract. They will always attract each other. And what happens if the current is anti-parallel? And if you have two anti-parallel currents, then they will repel each other. So always remember these 3 points. These two are extremely important for you to remember for all your subjective type questions, that parallel current attracts and anti-parallel current repel each other. So here if we go to the diagram, then you can see the currents as parallel. So in these two current carrying conductors, the current that is flowing is parallel, so they will always be attracting each other. Now the force we have calculated here is given as mu naught upon 2 pi. IA IB upon D into L. So if you divide this total force with the length, then we'll get the force per unit length. So if you divide this force on V due to A with the length of segment L, then you will have the force per unit length. So this will be equal to mu naught IA IB upon 2 pi D. These are the distance between these two. Then that will give you the force per unit length. So that means we can easily calculate the formula, what is magnetic field and what is the magnetic force, and what is the result, that also we know. So these two currents, they will be in ampere. This is the length will be in centimeter and this distance will be in centimeter. So from here we can define the definition. So from here we can define what an ampere is. So from this formula, if you want to get the definition of ampere, because this is an ampere, this is a constant, and these two are distant, so they will be in centimeter and they will cancel out. So this gives us that ampere is that value of steady current when maintained in each of the two very long, straight, parallel conductors of negligible cross-section and placed 1 meter apart in the vacuum. Then they produce a force of 2 into 10 to the power minus 7 Newton per meter of length. So how we got this definition? Let us see. Now we'll derive this definition from this formula. So this is force per unit length divided by, then this is equal to mu naught IA IB upon 2 pi D. So this D we can take as the distance, we can make as minimum, say maybe 1 meter. So we can write it down as 1 meter. So if you want to calculate, so if you want to define the value of ampere, then from this formula you can get that ampere is the value of the steady current, right? So that is how 1 ampere is defined. Next we'll do that when we place a current carrying loop in uniform magnetic field. So here we are taking a rectangular loop. As you can see, ABCD is our rectangular loop. You can see in the blue color in the diagram. So this is a loop ABCD and this loop is carrying the current I. You can see the direction of current that is shown in the diagram. Here you can see that this ABCD is the loop and this is the carrying the current. From here you can see it is in the upward direction going like this and then it is coming down here. So here you can see a source of the current. There is a cell which is connected and it gives the current to this loop. And this loop is kept in the magnetic field. That means we have two permanent magnets. That is north and south. You can see these shows two permanent magnets. And this loop is kept in the field of these two permanent magnets. And this magnetic field is uniform throughout the loop. So here we see the plane of this magnet. So the loop is placed in the same plane of the magnetic field. So we'll consider our first case when the loop is present in the plane of the magnetic field. So there is already a magnetic field B which is present. So we can show that this B is a magnetic field. This loop is already in the magnetic field. So if this rectangular loop is already in the magnetic field, that means it will experience a force. And this force we know is given by when there is a current carrying conductor and is placed in the magnetic field, then always we calculate the force from the formula IL cross B or ILB sin theta. So this is IL cross B we will use here. So now we'll apply this formula as is IL cross B for this rectangular loop. So first we see these 2 points, these 2 lines AD and BC. So AD and BC are horizontal and they are in the plane of the magnetic field, whereas AD and CD are perpendicular. So first we'll go for AD and BC. So we can write it down as for sides AD and BC. So for sides AD and BC, since this length of these two and the magnetic field is in the same plane, so that means if we write down F is equal to ILB sin theta, because IL cross B is ILB sin theta. So theta will be 0 degree because here this length L of these two AD and BC and the magnetic field is in the same plane. So theta is equal to 0 degree. So F is equal to ILB sin 0, 0. So force is 0. That means the force due to magnetic field on these two sides AD and BC will be 0. So now we are left only with sides AB and CD. So now we'll calculate for AB and CD. So we'll calculate for side AB first. These are the 4 arms of this rectangular loop. So for 2 arms which are horizontal, this force is 0. Now for the first vertical arm AB. So formula remains the same, F is equal to ILB sine theta. So here these are this vertical, so this is always perpendicular to this plane. So since this is perpendicular to the plane of magnetic field, theta is equal to 90 degree and sine 90 degree is equal to 1. So if we write down F is equal to ILB sine theta, then this sine 90 degree is 1, so this will become 1. So force on side AB is equal to I, the length of this side. Here you can see that this length is equal to B, where we have shown this B for the magnets. So this side is B and this side is B. Okay. So this is B and B is the capital. B will represent the magnetic field and sine 90 degree is 1. So force inside AB is F is equal to IBB, where small b is the length of the arm AB and capital B is the magnetic field. And if you want to know the direction of this force, this will be perpendicular to both L and B. So this is the length is perpendicular here, perpendicular to this plane and B is in this plane. So the force will be into the plane of the loop. Similarly, if we calculate for side CD, then force F is equal to ILB sine theta. Here again theta is equal to 90 degree. So again we'll get it as I, small b and capital B, because this will also have the length of small b. So these two force inside AB and force inside CD are same. They are IBB. So both these forces are IBB. And but here for side CD, if you calculate the direction, then the force is out of the plane of the loop. And how we got the direction? We got this direction only using the right hand rule. So if you use the right hand rule and the current for side AB, if you see, then the current is upward and the magnetic field is in this direction. So the force will be out of the plane. If you see for side AB, then the current is in this direction and the magnetic field is along this direction. So if you use the right hand rule and you spread your fingers, your index and middle finger in the direction of current and middle finger in the direction of magnetic field, then your thumb will point downward. So that will show the direction of force. So that is into the plane of the loop, that means downward. Similarly, if you use for side CD, if you point out your index finger downward and your middle finger in the direction of magnetic field, that is horizontal like this, then your thumb will point outward. So your thumb will show the direction of force. So that is how we get the direction of these forces on AB and CD. So these forces on AB and CD are similar. F is equal to I, small b into capital B. But for AB it is into the plane of the loop and for CD it is out of the plane of the loop. So here we are having two equal forces, but these are opposite to each other. So there is a pair of equal and opposite forces, and a pair of equal and opposite force always produces a torque. So there is a torque which will act on this rectangular loop ABCD. Two forces are working along its arms AB and CD. For AB, the force is downward into the plane of the loop, and for side CD, arm CD, the force is upward, it is out of the plane of the loop. So that is how it will a torque will act, and it will start rotating this rectangular loop in the uniform magnetic field. So if you run the net force, then these two forces on arm AB and arm CD are equal and they are in the opposite direction. So that gives us the net force is 0. But since these are opposite and equals, we get a torque. So we can write down torque. So is represented with the symbol torque. So the torque, so in order to write on the torque, we have to differentiate between these two forces. So force inside AB we can write on as F1, and force on side CD we can write on as F2. So now these are the two forces which are in the opposite direction. So we can say that this force F1 is acting and maybe in the downward like this. So this will be F1, and on side CD this force F2 will be acting out of this plane. So F2 will be going outward. And if I say this, and if this length we take as small a from here to here, so the distance between arm AB and CD is small a. So for AB it is force F1 and for CD it is F2. So here somewhere we can take a center. So this distance will be a by 2 and this distance will be a by 2. So now we can say that F1 will act on so now we can say that F1 will be acting for the distance a by 2 and here a by 2. So now we can write on the torque very easily. I'm drawing it here once again. Say this distance is a. Here we are having a force F1 going downward for this arm, and here force F2 which is going upward for this arm CD, and here we are having a center. So this distance will be a by 2 and this distance will be a by 2. So in order to write on the torque, we can use this simplest representation. So this is equal to F1 is acting on the distance a by 2 plus F2 is acting on the another distance a by 2, that is the second half. So put the value of F1. Value of F1 is IBB. So I small b capital B multiplied with a by 2 plus put the value of F2 I small b capital B multiplied with a by 2. How beautifully we have done this. So this is IAB small b b by 2 plus I small b b by 2. So this is half, and half and half. Half plus half gives us 1, right? So we will have this as I, A, B and B. Now A into B, this side is A and this side is B. So we can calculate the area of a rectangle. Area of a rectangle is A into B. For this rectangle, this is a rectangular loop. So A into B will give us the area. So A into B we can write on as area. So this is equal to I current into area into magnetic field. So that is the torque. Torque is equal to IAB, because AB is equal to area of rectangular loop. So capital A is the area of the rectangular loop. So we have written this IAB. And here we are having a single rectangular loop. If you are having a coil or if you are having a number of N turns, then for torque you have to multiply it with N. So in that case we write down torque is equal to B, I and A. And it's very easy to remember because Bina is the name of someone, maybe one of your friends. So you can say that torque is always Bina. Whenever we place a rectangular loop in a uniform magnetic field, then the torque acts as Bina. N is the number of turns, A is the area, I is the current, and B is the magnetic field. So always remember torque is Bina, and torque is Bina, right? Now we consider the second case. So in this case, our rectangular loop is not in the plane of B, and the force which is acting on AB is F1, force that is acting on CD is F2. So we want to calculate the torque here. As you can see that the magnetic field is along this direction and this loop is at any angle theta from the magnetic field. In the previous case, this rectangular loop and magnetic field B are in the same plane, were in the same direction. Now we have tilted this rectangular loop with any angle theta. So there will always be a torque acting between AB and CD, because AB and CD are having the same force F1 and F2 and they are acting in the opposite direction into the plane and out of the plane of the paper. So the net force is 0, but there is a tilt, so there is always a torque which is present, but this torque is less than the torque in the previous case. How come it is less than? Let us find out. So we will say that this rectangular loop is tilted, so we have drawn a line like this, not a perfect horizontal line as in the previous case, and we are having F1 and F2. So here we have tilted it somewhat, and here the force F1 will be acting downward and F2 will be acting upward. If you draw a perfectly horizontal line, it will be going like this. So from here, say if this total distance is A now, this tilted line is A. So you can divide it into A by 2 and A by 2 here, and here's the midpoint. So if this is a horizontal line and if I drop a normal over here and a normal over here, so this angle is say theta. Is at any angle theta. So if you take this A by 2, if you take the component, this will be A by 2 sine theta, and this will again be A by 2 sine theta, right? So this is A by 2 sine theta and this is A by 2 sine theta. So now we can write down torque very easily. So torque, total torque will be F1 into this is distance is A by 2 sine theta. From here to here, the distance A by 2 sine theta up to the midpoint. And again, if you move from the midpoint to the point of action of force F2, now this is again F2 multiplied with A by 2 sine theta. So in the previous case, we were having A by 2 and A by 2 only. Since the angle was not present there, they were perfectly horizontal. So, but here in this case, it is tilted at any angle theta. So we take the vertical component, that is A by 2 sine theta, and here again A by 2 sine theta, that is the vertical component we have taken for the side. So our total torque comes out to be, this is A by 2 sine theta plus A by 2 sine theta. So this is equal to, if you put the value of force, then this is IBB, and A by 2 sine theta plus A by 2 sine theta will give you A sine theta. So this half and half will make a full. So this is the total force that is acting. Again, if you take this small b into small a into b will give you the area of the rectangle, that is capital A. That is the area of rectangular loop. So if you put the value, then you get the value of tau as IAB sine theta. The sine theta is because we have tilted an angle. So in the previous case, we were not having this value sine theta. We were only having IAB. So sine theta, as you know, it varies from 0 to 1. The maximum value for sine theta is 1. So whenever this is 1, the maximum value, then tau is equal to IAB. That was in the previous case, but if it is less than 1, it is half or 1 by 4 and root 3 by 2, then always this tau will be less than the previous value. That is why we have said that this torque will be less than the previous values. It can have the maximum value of that will be equal to the previous value. So that is all due to the sine theta. So we got tau is equal to IAB sine theta. So what this torque will do? This torque will try to rotate this rectangular loop, rotate, and when this torque will become 0, because the current is not becoming 0. If you look in the formula, the area of rectangle is not going to be 0, the magnetic field is not going to be 0, only this theta can be 0. So when this tau will be 0, when this sine theta will be 0. And sine theta is 0 with theta equals to 0, then sine theta will be always equal to 0. So that means if the theta is equal to 0, then this torque will stop acting. So that means if this theta will become 0, that means whenever this loop comes into the plane of the magnetic field, then this torque will stop acting. That means we can write it down as torque acts till the value of theta becomes 0, or theta is equal to 0 degree. And what happens at 0 degree? If this theta is equal to 0 degree, that means the rectangular loop is in the same plane of B, or rectangular loop and magnetic field B are parallel to each other. That means the plane of rectangular loop is parallel to the magnetic field B. That was our first case. So in the second case, the torque will act till the rectangular loop becomes parallel to the existing uniform magnetic field B. So since there is a magnetic field, we can also calculate the magnetic moment of the loop. It's a new quantity, so pay attention to this, that how we are calculating the magnetic moment. In electrostatics, we calculated the electric dipole moment. Similarly, we will calculate the magnetic moment. So the magnetic moment is represented with the symbol small m, and the formula is I into A. That is current into area. I is in ampere and the area is always in meter square. So the unit of magnetic moment will be ampere into meter square, and the formula is magnetic moment is equal to IA. Always remember, magnetic moment is equal to I into A. This simple formula will always give us the magnetic moment. So just go to the tau we have just derived. We have derived this tau as IAB sine theta. And I into A will become the magnetic moment. So this is equal to MB sine theta. Because from the new formula M is equal to IA, we can write down this IA is equal to M. So this is MB sine theta, and if there is a sine theta, that means a cross product. So we can write down a cross product between M and B, that is the magnetic moment, and this is the magnetic field. So tau is equal to M cross B. So now we have the formula tau is equal to M cross B. So you can write down tau in terms of current, area, magnetic field and sine theta, or you can write down tau in terms of magnetic moment and magnetic field. Now when this tau will become 0, this magnetic moment cannot become 0, magnetic field cannot become 0, only the sine theta can become 0. When this will become 0, when theta is equal to either 0 degree or theta is equal to either 180 degree. As in the previous case, as I told you that when the plane is parallel to B, so either it is parallel or anti-parallel, the theta will become 0, either it is 0 degree or it is, you can also say it is, you can take it as 180 degree. So whenever you have theta 0, 180, then either it becomes parallel or anti-parallel, then it is 0. So similarly here the tau will become 0 when theta equal to 0 degree or 180 degree. So sine 0 is 0, sine 180 is 0. So then tau will become 0. That means the magnetic moment is parallel to B or the magnetic moment is anti-parallel to B, right? So in this case the tau vanishes, and this M is equal to IA. And if you are having N turns, then how will modify? So you can write down for N turns. Here we are taking a rectangular loop which is having only one turn. So if there are N turns, then this current will be multiplied with N, because this current is flowing in a single loop. If there are capital N turns, the current will flow into capital N loops. So tau will become BINA sine theta when it is not in the plane of the magnetic field. So tau is equal to BINA or tau is equal to BINA sine theta, right? Always remember this for a rectangular loop in a uniform magnetic field, external magnetic field. And also this our magnetic moment will become NIA, because now the current is not flowing in a single loop, it is flowing in N loops. So this, always remember that when you are given with N turns, you have to simply multiply what formula you already know. Just multiply with N, because now the current is not flowing. Simple logic, because now the current is not flowing in a single turn, it is flowing in N turns. So not I, NI. Here also not I, it is N multiplied with I. So NIA and BIN is sine theta. So that is how you can easily modify when you are given with N turns. So you can make it capital N terms. So whenever you are giving with capital N terms, then your equations are modified in this way. Remember this, and it will make much easier for you to modify your equations and perform them correctly. Next thing we are going to study is magnetic dipole. So we want to define the magnetic dipole in form of the circular current loop, because we have already calculated the magnetic field due to a circular current carrying loop. So we'll use the same formula here. We'll not do the derivation again. If you want to know how we have derived this formula for the circular current carrying loop, you can refer to my lecture. That is again on the magnetism, our lecture 1. So the link is given below in the description box. Just quickly go to that and you will see whole of the derivation, because direct away we are going to use that formula here, because that is a very important derivation. You will use it in theory, you will use it in your numerical problems, and you have to always remember the formula. But if you want to go to the details of the derivation, you can go in here. Here we will use the direct formula. So let us use the formula that a magnetic field due to a circular loop of radius capital R, which is carrying a current I, and the magnetic field along the axis is given by P is equal to mu naught I R square upon 2 R square plus X square to the power 3 by 2. This is the formula we are writing down direct away. And the direction is along the axis of the loop. The direction of magnetic field is along the axis of the loop. This we have done in detail, so we are not doing it again. And we do this using the right hand rule. We find out the direction using the right hand rule. Now if the distance x, that is the distance from the center to the point P where we want to calculate the magnetic field, if this distance is very greater than the radius R of the loop, then we can modify this as, because x is having a very large value, so we can neglect R here so we can neglect R here in comparison to this x, and what we get is B is equal to mu naught I R square upon 2. This is x square to the power 3 by 2. So this 2 cancels out, 2x cube. So this is the formula that is modified for x is very greater than R. Now we can write it down as, we can multiply it with 2 pi and divide with 2 pi. So this will be mu naught I pi R square So we have multiplied this with pi and divided with pi. So mu naught I pi R square upon 2 pi x cube. Why we have done this? Because pi R square will give us the area. So this is the area of a circular loop. So this is mu naught I A, where A is equal to pi R square, the area of the circular loop, and 2 pi x cube. Here you can write down A is equal to pi R square, that is the area of a circular loop. Now we have just studied the new relation that the magnetic moment M is equal to IA. Now you will understand why we multiplied with pi and divided with pi, because we want to get the area A. Whenever we want to introduce a new thing, we want to have that formula. So we were interested in having the formula I into A. I we are already having, we want to make A. So if you divide with pi, we will have A. So I into A now we can replace with M. That is why we have done this exercise, multiplying and dividing with pi. So now we have IA. So in place of IA, what we will put? In place of IA, we will put M, small m, that is the magnetic moment. So put M is equal to magnetic moment in this formula. So what you get? B is equal to mu naught M. M is I into A, the magnetic moment, new formula, upon 2 pi x cube. So this is the formula we have derived. So this formula is correct, but what happens whenever we are using this, we always use this mu naught in the terms of mu naught is equal to 4 pi into 10 to the minus 7. So if you want to make it 4 pi here, then you can write down B is equal to mu naught upon 4 pi. Since you have divided with 2, so you have to multiply with 2. So 2m upon x cube. Right? So this is the formula we get for magnetic field of a circular loop in terms of. So this is the formula we get for magnetic field in terms of the magnetic moment. P is equal to mu naught upon 4 pi 2m upon x cube. And if you compare this formula to the electric dipole, so for electric dipole, that is in the electrostatic we have studied, that for electric dipole we had the formula E is equal to magnetic field E is equal to 2p upon 4 pi epsilon naught x cube. similar, just similar. 2 electric dipole upon 4 pi epsilon naught x cube, then 2 into magnetic dipole upon 4 pi upon mu naught x cube, right? So this is 2 multiplied with electric dipole, this is 2 multiplied with magnetic dipole. This is upon 4 pi x cube and this is upon 4 pi x cube. Always remember that these two formula are equal to their electrostatic counterpart. So whatever formula you are having in the electrostatic, similar formulas you will have in the magnetism. So what you get is, the only difference is that always remember in electrostatic you will have 4 pi epsilon naught and here you will have 4 pi upon mu naught. Because in electrostatic 4 pi epsilon naught is a constant, that 1 upon 4 pi is equal to k is equal to 9 into 10 to the power 9, and here mu naught upon 4 pi is a constant, that is 10 to the power minus 7, right? So in magnetism you will always have constant as mu naught upon 4 pi. In electrostatic you will always have constant as 4 pi epsilon naught. Rest everything is same. This is 2 magnetic moment, 2 electric dipole moment, and this is x cube, this is x cube, right? So this is the magnetic field at the axis of the circular loop, and if you take any point on the middle which is in the plane perpendicular, then for electrostatics we are having, for perpendicular bisector we were having, if you remember the formula, we were having E is equal to P upon 4 pi epsilon naught x cube. Rest everything is same, that instead of 2p we are having only single p, right? So if you want to convert this electrostatic formula into its magnetism counterpart, so can you do? Let us try, we will try, and if you are able to do it right, then it will be much easier for you to remember. Let us try. So E electric field, that means we are having magnetic field here. So this is equal to P, that is electric dipole. So we'll have the magnetic dipole M here. And here it is 4 pi epsilon naught. So we will have 4 pi upon mu naught. Because in magnetism we always have 4 pi upon mu naught. Then it is x cube. So we can write it down as x cube. Have we done it right? Yes, we are right. So this is the magnetic field at the perpendicular bisector. If you take a plane which is perpendicular to the axis of the circular loop and passing from the center of the axis of circular loop, then you have the magnetic field as mu naught m upon 4 pi x cube. And that is the magnetism counterpart of its electrostatic. So these are the two magnetic fields at the center of the circular loop, as well as the plane which is passing from the center and perpendicular to the axis of the loop. So we can write on magnetic field in both the cases very easily. Only we have got the formula from the electrostatic counterpart. So these are the two formula for the magnetic moment. You can write down the magnetic field in terms of the magnetic moment. So these are the two formula we have written. Now here I want to tell you a very important thing, and you have to note down this thing. So just make a note. Because here we are talking about the electric dipole and the magnetic dipole. So let us first talk about electric dipole. So what is an electric dipole? Electric dipole we say it is a pair of two equal and opposite charges placed at some distance. So an electric dipole is built up of two electric monopoles. Di means two, so it is built up of two electric monopoles. That means two charges which are equal and opposite in sign. So each charge we call as a monopole. So if you are having plus q, that is a monopole, and minus q, that is a monopole, and these are at some distance, then we call them an electric dipole. What if we come to the magnetic dipole? Then this magnetic dipole is only a current loop. because magnetic monopoles does not exist. There is not anything in the world you can call as magnetic monopole. There is no single polarity, no monopole exists for the magnetism. It will always be a magnetic dipole. So whenever you are calling about or whenever you are talking about any magnetic dipole, you are talking in terms of the current loop. You are not talking about two individual magnetic monopoles. So in magnetism, no monopoles exist. Only there is a magnetic dipole that is in the form of current loop. So that is the note for today. Note it down and keep moving. So let us go to the example of magnetic dipole to make it much clearer. Let us quickly move to an example of magnetic dipole. So write down example of magnetic dipole. So write down example of magnetic dipole. So in order to understand the example of magnetic dipole, we have to take any current loop. That means a charge that is flowing, and if we are talking in terms of current, we always take an electron. So let us take an electron which is revolving in a circle. So this is an electron. This is the center, and if you take the radius, smaller is the radius. This is the current loop because electron is flowing. Electron is moving like this. So this is, you can say, is a current carrying loop. So this electron is performing a uniform circular motion and it is moving around a stationary heavy nucleus. So this is a nucleus and it will have a charge of positive. Let us say that is the number of protons. So we will say that the total charge on this stationary heavy nucleus is plus Ze, and this is electron, a single electron which is revolving around this stationary heavy nucleus at a distance small r. So now if the electron is flowing, then we can easily calculate the current because I is equal to Q upon T. Q is E here, so E upon T. So this is the current. And if you want to take the time period for one revolution, then you can take it as capital T. So take this T as a capital T. Why we are taking capital T? Because we are taking it as a time period for one complete revolution around the stationary nucleus. And this time that will be taken will be the distance travel in one rotation. Since this is a circle, so the distance travel in one rotation is 2 pi r. R is the radius and the velocity, say v is the velocity. So this time is equal to distance upon velocity. So this is the distance travel in one rotation and this is, say, the velocity of this moving electrons which is moving in a circle. So from here we can put the value of T into this. So the current will be I is equal to E upon 2 pi r upon V. So I is equal to EV upon 2 pi r. Now finally we want to calculate the magnetic moment. So magnetic moment also has a symbol mu. It is represented with the symbol small m, but it also has one more symbol, that is mu, and it is corresponding to electrons. So we write it down as mu e. Mu e always corresponds to the magnetic moment of an electron. So the formula will remain the same. It is I into A. I is the current and A is the area, right? So I is the current. We have just calculated EV upon 2 pi r. We have put the value, and area of the circle will always be pi r square. So multiplied with pi r square. So pi cancels out, 1 r cancels out. So this is EVR upon 2. So the magnetic moment of any electron which is moving in a circle around the stationary nucleus is EVR upon 2. That is the magnetic moment of any electron because we have calculated it using IE as a simple formula. Mu is equal to EVR upon 2. This is very important formula. Always remember this. And this direction of magnetic moment is into the plane of the paper. One another way which we can write down this magnetic moment is just look into it. So another way of writing the magnetic moment. because we have just calculated the magnetic moment of electron is equal to EVR upon 2. So if I multiply this with the mass of the electron and divide it with the mass of the electron, and it is E here, and this is mass of electron VR upon twice mass of electron. So this MVR, we can write it down as, this MVR is the angular moment of the electron about the nucleus, which we call as orbital angular momentum. So this L, we can write it down as orbital angular momentum of the electron. So this mu E will become E into L upon 2me. And what is L? L is the orbital angular momentum of electron. So whenever you are having positive charge, you have mu is equal to EL upon 2me, and whenever you want to write it down the negative charge of the electron, then it will be minus E upon 2me and multiplied with the orbital angular momentum. And why we are having this? Because this orbital angular momentum L is directed opposite to the magnetic moment. If you see this L and then mu E, then there is a negative in these two, negative sign between these two. So this orbital angular moment of the electron and the magnetic moment of the electron, these are in the opposite direction. But whenever you are having a positive charge, then mu is equal to E upon 2me into L. That means it is having a same direction. Orbital angular momentum and magnetic moment are having the same direction for a positive charge. And if you take the ratio of these two, magnetic moment of electron divided with the orbital angular moment of electron, then this will be E upon 2me. This is known as gyromagnetic ratio. If you are planning for any of the competitive exam, IIT, JEE, then you should remember what is this gyromagnetic ratio. Gyromagnetic ratio is the ratio of magnetic moment of the electron to the orbital angular momentum, and its value is constant. It is 8.8 into 10 to the power 10, and this is the charge, so this is in coulomb, and this is the mass, so it will be in kilogram. And this is only for this value is only for electron. So for electron, if you want to calculate the gyromagnetic ratio, then this is equal to E upon 2me. This is the magnetic moment divided with the orbital angular momentum, and the value is E upon 2me, and we get it as 8.8 into 10 to the power 10 coulomb upon kilogram. And if you apply the Bohr quantization, although you have studied in your 11th standard, but I don't know how much you remember. So if it is a Bohr quantization, Bohr is the name of the scientist, and quantized means that any physical quantity will have a definite value, that is known as a quantized discrete values. Definite discrete values, and we call it as a quantization. So this orbital angular momentum has quantized value. That means it is always in the multiple of 1h upon 2 pi. And n is any integer. You can vary this value and you can have discrete value, that is known as a quantization. Say for example, if you put n equals to 1, then the value is h upon 2 pi. If you put 2, then it is 2h upon 2 pi, that is h upon pi. If you put n equals to 3, then it is 3h upon 2 pi. So this orbital angular momentum will have values only h upon 2 pi, h upon pi, 3h upon 2 pi, 4h upon 2 pi, h upon 2 pi, that is 5h upon 2 pi. So there are no intermediate values. It will have only discrete value, that is known as a quantization. So L is equal to nh upon 2 pi, that we call as Bohr quantization, where n is any integer. It is having the value of 1, 2, 3 and so on, any integral value. So that is a Bohr quantization. So if you put this Bohr quantization into this gyromagnetic ratio, then you will have mu E is equal to E upon 2me from this formula, and the value you can put as nh upon 2 pi. So now put all the values. The charge on electron is 1.6 into 10 to the power minus 19 coulomb. The value of h, that is Planck's constant, is 6.62 into 10 to the power minus 34. And then value of 4 pi, this is 2 and 2 pi, so that will become 4 pi. So 4 into 3.14. And if you want to put the mass of electron, then it is 9.1 into 10 to the power minus 31 kilogram. We will have, if you calculate this total value, it comes out to be 9.27 into 10 to the power minus 24 ampere into meter square. So this is the minimum value, because here we have taken n equals to 1. So we call it as a minimum value of the magnetic moment of electron. Minimum value. If you put n equals to 2, 3, 4 and so on, then you will have the higher values. So this is the minimum value. So today we have learned very interesting thing in this derivation, that's mu e, that the magnetic moment of electron is EVR upon 2. And if you multiply and divide it with the mass of the electron, then you can put this L as the orbital angular momentum, and the ratio of magnetic moment and the orbital angular momentum is E upon 2. That is the gyromagnetic ratio. It is a very important quantity, and now we know its value. We can also do the quantization of this orbital angular momentum L. Then quantization is in the terms of h upon 2 pi. So this orbital angular momentum we can write down as nh upon 2 pi, and if you put the value of L in the terms of h upon 2 pi, we have taken n equals to 1, so we get the minimum value of magnetic moment of electron, and that comes out to be 9.27 into 10 to the power minus 24 ampere to meter square. So all these things are very much important. Take a screenshot, always remember this thing. These are the small quantities, and that corresponds to the magnetism. So, and they come under the magnetic moment of an electron. That is a very small derivation, and it contains at least 3 to 4 important quantities that will be very helpful for you in all your competitive exams. If you remember these small things, these basics, you will never fail in doing everything right. So always remember, keep them writing, always write down the things, and then to always remember the basics. So all the best from my side, and keep on sharing, commenting. If you are not able to get anything, if you want to know in addition, then please comment me in the inbox. I'll try to answer all your queries. So that's all for today. If you like this lecture, then like and share and subscribe to our channel Physics Class, which is now becoming favorite for the students for the basics as well as for the numerical part. So just subscribe it and like and share it so that you get notifications daily for new such lectures, for all the additions. So all the best from my side. Thank you.